You were told the earth is stable, that mountains stand forever, that continents don't move, that everything you see around you, the landscape, the cliffs, the valleys, is simply scenery. That is not true. The earth is a planet that constantly destroys and rebuilds itself. Right now, while you are watching this, Africa is splitting into two separate landmasses. Right now, the floor of the Pacific Ocean is sliding beneath North America at roughly the speed your fingernails grow. Right now, the San Andreas Fault is accumulating stress for an earthquake that will reshape the western coastline of the United States. And the great canyons and rifts of this world, those spectacular places that end up on postcards and desktop wallpapers, are not simply beautiful accidents of geography. They are scars, and every scar is a clue. Today, I want to show you what those clues say about our planet's past and what they predict about its future. Before we go any further, please subscribe to this channel. Your support is what makes this work possible, and I genuinely appreciate it. Thank you. Let's start with something you think you already know. The Grand Canyon, one of the most photographed places on Earth, roughly 277 miles long, up to 18 miles wide, more than a mile deep. Every year, roughly 6 million people stand at its rim, take a photograph, and feel something they can't quite articulate. A kind of vertigo that has nothing to do with the drop. What they're feeling, without knowing it, is time. Because the Grand Canyon is not primarily a geographical feature. It is a clock, the most legible clock on the surface of this planet. Here is how to read it. When you stand at the south rim of the Grand Canyon and look down, you are not simply looking at rock. You are looking at pages. Each layer of rock is a chapter. Each boundary between layers is a gap in time. Sometimes a small gap, sometimes an incomprehensible one. The tan and cream-colored Kaibab limestone at the very top, the layer you're standing on, was laid down roughly 270 million years ago, when this region was a shallow tropical sea near the equator. 270 million years ago. The dinosaurs had not yet evolved. The first mammals were still tens of millions of years in the future. And you are standing on top of that moment, looking down. As your eye descends the canyon wall, you move backward through time. The reddish Hermit Formation, 280 million years ago, a coastal floodplain. The Supai Group below it, 320 million years ago, river deltas and tidal flats. The Redwall Limestone, 340 million years, a warm, clear sea teeming with crinoids and brachiopods. Each layer tells you what this place was. Each layer is a different world, occupying the same coordinates on the map. But then you reach something that stops geologists cold every time they see it. Roughly halfway down the canyon, the neat horizontal layers end. And what lies beneath them is not another horizontal layer. It is a tilted, eroded surface of much older rock. The Tonto Group, the Bright Angel Shale, the Tapiz Sandstone. And beneath even those, at the very bottom of the canyon, near the banks of the Colorado River, you find something that changes the scale of everything. The Vishnu basement rocks. The Vishnu schist. Dark, almost black, twisted into wild folded patterns by heat and pressure, cut through with pink veins of granite. These rocks are 1.7 to 1.8 billion years old. 1.8 billion years. Let that settle for a moment. When those rocks formed, there was no complex life anywhere on Earth. Not even simple multicellular life. The most advanced organisms on the planet were single-celled microbes, prokaryotes and the earliest eukaryotes, drifting in shallow seas. The continents were arranged in configurations that no geologist alive today can describe from personal experience. The day was shorter, the moon was closer, the atmosphere contained almost no oxygen, and the rocks at the bottom of the Grand Canyon were already ancient mountain roots, deeply buried, cooked and twisted by the pressures of continental collision, then slowly cooled as the mountains above them eroded away over hundreds of millions of years. But here is the detail that most visitors never learn. Between the Vishnu schist at the bottom and the Tapiat sandstone just above it, between those 1.8 billion-year-old rocks and the 520 million-year-old rocks sitting on top of them, there is a gap in the rock record. The boundary between them is called the Great Unconformity, and it represents approximately 1.2 billion years of missing time. 1.2 billion years. Gone. Not present in the rock. Either never deposited or deposited and then eroded away so completely that nothing remains. This boundary, this single line you can put your finger on in the canyon wall, represents a gap in Earth's history longer than the entire span of complex animal life on this planet. Everything from the Cambrian explosion to today takes up roughly 540 million years. The Great Unconformity swallows more than twice that, and geologists have been arguing about what happened during those missing billion years for over a century. The leading hypothesis today involves snowball Earth. The evidence suggests that between roughly 750 million and 600 million years ago, Earth experienced one or more episodes of near-total glaciation. The entire planet, including the equatorial oceans, covered in ice. The glacial erosion that accompanied these events was catastrophic. Ice sheets kilometers thick scoured the continents, grinding down rock that had accumulated over hundreds of millions of years and carrying it into the oceans. When the ice melted, the eroded surface was left behind, not as a layer, but as an absence. A clean, flat wound in the geological record. The Great Unconformity may be, in part, the scar left by snowball Earth. And the Grand Canyon just happens to expose it so clearly that you can see it with your naked eye from the rim across the canyon on a clear morning. Now, the Grand Canyon is one of the most thoroughly studied geological features on Earth. But it is fundamentally a passive record, a place where the Colorado River has cut down through the layers and exposed what was already there. It is history. It is a library. What it is not is active. What it is not is alive. For that, you need to go to Africa. The East African Rift System is not history. It is the present tense. It is the future tense. It is the most dramatic geological event currently happening on the surface of this planet, and the vast majority of people have never heard of it in any meaningful depth. Here is what is happening. The African continent is being torn apart. Not metaphorically, not gradually in some way that requires millions of years to become apparent. It is measurably, demonstrably, actively splitting along a system of faults and rift valleys that extends from the Afar Triangle in the north, where Ethiopia, Eritrea, and Djibouti meet, southward through Kenya, Tanzania, Malawi, and Mozambique, for a total length of roughly 3,000 miles. The East African Rift System is the embryo of a future ocean. What is happening in East Africa today is exactly what happened 180 million years ago, when the supercontinent Pangaea began to break apart. The same process, the same geometry, the same physics, just at an earlier stage. To understand what a rift is, you need to understand what happens when the mantle beneath a continent decides it wants to go somewhere. Deep in the Earth's mantle, convection currents carry heat from the interior toward the surface. When a particularly hot upwelling, a mantle plume, rises beneath a continent, it does several things simultaneously. It heats the crust from below, causing it to expand and dome upward. It weakens the crust, making it more susceptible to faulting. And it pushes laterally outward, stretching the crust like taffy being pulled from both ends. When the crust stretches far enough, it fractures. Blocks of crust drop down along the fracture lines, creating a rift valley, a long linear depression flanked by high escarpments. The East African Rift System has created some of the most dramatic topography on the African continent. The Ethiopian highlands rise to over 14,000 feet. The Rift Valley floor in some places sits more than 3,000 feet below sea level. Lake Tanganyika, which sits in the rift, is the world's longest freshwater lake and the second deepest, reaching depths of over 4,700 feet, and it is getting longer and deeper every year. The escarpments flanking the rift in places rise nearly a mile above the valley floor, in what amounts to a geological cliff face, exposing the layers of volcanic rock and ancient basement that record the rift's history. And the rift is spreading. Not quickly by human standards, the East African Rift opens at roughly 1/4 of an inch per year in most places, and up to an inch per year in the Afar region. But over geological time, this rate is significant. In roughly 20 million years, if current rates continue, the eastern fragment of Africa, the Horn of Africa, and the land east of the rift will separate from the rest of the continent. The Indian Ocean will pour into the widening gap. A new sea will form, narrow at first, like the Red Sea is today, then widening over tens of millions of years into a full ocean basin. The map of Africa will be permanently redrawn. We know this because we have a precedent. The Red Sea itself is a young ocean, perhaps 30 million years old at most. It formed by exactly this process. The Arabian Peninsula was once attached to Africa. The same mantle plume that is driving the East African Rift System drove the separation of Arabia from Africa, beginning roughly 35 million years ago. The Red Sea is what the East African Rift will eventually look like. A narrow, elongated body of seawater between two recently separated continental fragments. And one day, millions of years further on, it will look like the Atlantic, a mature ocean separating continents that have drifted thousands of miles apart. In the Afar Triangle, that low-lying, brutally hot desert region in northeastern Ethiopia, the geometry is particularly extraordinary. Three rift systems meet at a single point. The East African Rift coming from the south, the opening of the Red Sea to the northeast, and the Gulf of Aden Rift to the east. This triple junction is a place where the crust is being pulled in three directions simultaneously, and the result is a landscape unlike anywhere else on Earth. The ground is below sea level. Volcanic calderas dot the landscape. The rock underfoot is so young, so recently erupted, that it still has a glassy sheen. And in some places, the crust has thinned to the point where it barely qualifies as continental crust at all. It is transitioning toward oceanic crust, the thin, dense basaltic crust that underlies the world's ocean floors. In September of 2005, a remarkable event occurred in the Afar. Over the course of just a few weeks, a series of earthquakes and volcanic eruptions opened a rift 60 kilometers long and up to 8 meters wide in the desert floor. 8 meters, 26 feet, in a matter of days. Rock that had been continuous for millions of years simply tore apart. Scientists who were working in the region at the time described hearing the ground crack, seeing fissures open underfoot. Satellite measurements confirmed what they were seeing. The African and Arabian plates had lurched apart in one of the most dramatic geological events recorded in the modern era. And then, silence. The ground stopped moving. The fissures remained, and the rift continued its slow, patient work. But let me now take you somewhere that most people have never seen and never will. Because while the Grand Canyon and the East African Rift are visible, accessible, photographable, the greatest scars on this planet are hidden. They lie at the bottom of the ocean. The mid-ocean ridge system is the longest mountain range on Earth. At roughly 45,000 miles in length, it encircles the globe like the seam on a baseball, running through every ocean basin. The Mid-Atlantic Ridge, the East Pacific Rise, the Indian Ocean Ridge, the Arctic Ridge. And most of it lies 2 to 3 kilometers below the ocean surface, unseen, in perpetual darkness, under crushing pressure. The mid-ocean ridge is where new oceanic crust is born. It is the engine of plate tectonics. It is the most volcanically active feature on the planet. Here is how it works. At the ridge's center, the rift valley at the crest, the two plates on either side are being pulled apart by the same convective forces we discussed in East Africa. As they separate, magma from the mantle wells up to fill the gap, erupting on the ocean floor as basaltic lava, cooling rapidly in the near-freezing water and solidifying into new oceanic crust. This process, seafloor spreading, has been occurring continuously for hundreds of millions of years. constantly creating new ocean floor at the ridges and pushing the older floor outward toward the continental margins. The result is something that initially seems counterintuitive. The ocean floor is not old. The oldest oceanic crust on Earth, found in the Western Pacific, is only about 180 million years old. By contrast, the oldest continental rocks are over 4 billion years old. The ocean floor is young. It is constantly being recycled. At the mid-ocean ridges, it is born. At the subduction zones, where oceanic crust dives beneath continental crust or beneath another oceanic plate, it is destroyed, pulled back into the mantle and re-melted. This conveyor belt, creation at the ridge, destruction at the subduction zone, is the fundamental cycle of plate tectonics. And its consequences are written in every geological feature we have discussed so far. The Grand Canyon's layers record ancient marine environments that existed because oceanic crust was being subducted, allowing the sea to advance and retreat across the continent. The East African Rift is the beginning of a new spreading center, a new addition to the mid-ocean ridge system. The world's oceans are shaped by the geometry of where the ridges are and how fast they spread. But there is a dimension to the mid-ocean ridge that receives far less attention than it deserves, and it has nothing to do with the movement of plates. It has to do with life. In 1977, the research submersible Alvin, operated by the Woods Hole Oceanographic Institution, descended to the Galapagos Rift, a spreading center in the Eastern Pacific. The geologists on board were looking for evidence of hydrothermal activity, hot water venting from the sea floor along the rift. They found it. But what they also found, completely unexpectedly, was an ecosystem. An entire community of organisms living in total darkness, at crushing pressure, in water superheated to hundreds of degrees Fahrenheit around the hydrothermal vents. Tube worms up to 8 feet long, clams the size of dinner plates, crabs and shrimp and fish, all living in a world with no sunlight, no photosynthesis, sustained entirely by chemosynthesis, the process by which bacteria use the chemical energy in hydrogen sulfide from the vent fluids to produce organic matter. This discovery fundamentally changed our understanding of where life can exist, and perhaps where life began. The hydrothermal vents at the mid-ocean ridges are not peripheral curiosities. They may be the cradles of life itself, environments where the chemical gradients, the mineral richness, and the energy sources necessary for the origin of life were present 4 billion years ago, sheltered from the bombardment raging at the surface. Every scar on the ocean floor, every hydrothermal vent field, every black smoker chimney pouring superheated mineral-rich water into the cold dark. Each of these is a potential window into the conditions that gave rise to biology. And speaking of things that are very much alive in ways you'd prefer they weren't, let me bring you back to dry land, specifically to California. The San Andreas Fault is, in some ways, the most famous geological feature in the United States. Not because it is the most dramatic to look at, which it isn't, but because it sits beneath one of the most densely populated regions in the world, and it is, by any reasonable assessment, overdue for a very large earthquake. But the San Andreas is more interesting than its reputation for catastrophe suggests. It is a window into one of the most important and least understood types of tectonic boundary on Earth. Most people, when they think about plate boundaries, think about two plates colliding or pulling apart. Subduction zones, spreading centers, mountain ranges. But there is a third type of boundary, and the San Andreas Fault is the most prominent example on land. A transform fault, where two plates slide horizontally past each other, neither colliding nor separating. The Pacific Plate, on the west side of the fault, is moving north-northwest relative to the North American Plate. Los Angeles, which sits on the Pacific Plate, is moving towards San Francisco, which sits on the North American Plate at roughly 2 inches per year. In roughly 15 million years, if nothing else changes, Los Angeles will be adjacent to San Francisco. The San Andreas Fault system runs roughly 800 miles through California, from the Salton Sea in the south to Cape Mendocino in the north. In places, it is clearly visible at the surface. A linear valley, a low ridge, a series of elongated ponds and displaced stream channels that betray the lateral movement of the ground. In the Carrizo Plain, a remote section of the fault in San Luis Obispo County, the surface rupture from historical earthquakes is so well preserved in the dry climate that you can see individual stream channels that have been offset by dozens of feet. The land on one side of the fault has moved relative to the land on the other side, and the streams that once flowed straight across the fault have been kinked into right angles. The total offset along the San Andreas system, the total amount of horizontal movement that has occurred since the fault first formed roughly 30 million years ago, is approximately 350 miles. 350 miles of accumulated displacement, written in the offset geology of California. If you could undo all that motion and slide the Pacific Plate back southward by 350 miles, rocks on the two sides of the fault would match up exactly. The same granites, the same metamorphic terrains, the same ancient seafloor sequences, currently separated by hundreds of miles, would be reunited. But the San Andreas is more than a single fault. It is a system, a broad zone of parallel and branching faults, some of which are just as dangerous as the main trace. The Hayward Fault, running along the eastern shore of San Francisco Bay through Oakland and Berkeley, is arguably more hazardous than the San Andreas itself, because it runs directly through one of the most densely urbanized areas in California. The last major rupture of the Hayward Fault was in 1868. The fault has been accumulating stress ever since. Geologists estimate that a full rupture of the Hayward Fault could produce a magnitude 7 earthquake affecting a population of several million people, with damage concentrated in areas built on the soft bay mud that amplifies ground shaking to extraordinary levels. The 1906 San Francisco earthquake, the one that most people remember, was a magnitude 7.9 rupture of the northern San Andreas Fault, breaking the surface for approximately 300 miles. The shaking lasted roughly 45 to 60 seconds. The fires that followed, ignited by ruptured gas lines and burning for 3 days, destroyed more of the city than the earthquake itself. Approximately 3,000 people died. The total displacement of the ground along the fault during that event, the amount the Pacific plate lurched northward relative to the North American plate in less than a minute, was up to 20 feet in some locations. 20 feet in 60 seconds. That is the difference between the slow and the sudden. The San Andreas creeps northward at 2 inches per year. But it does not always creep. Sometimes it snaps, and the energy stored in years, decades, centuries of accumulated elastic strain releases in moments, transmitted through the rock as seismic waves, felt by millions. But here is something that almost nobody talks about when they talk about impact craters. And it changes the way you think about scars entirely. In 2019, a team of researchers drilling into the Chicxulub impact crater, not the canyon, not the rift, but the buried scar of the asteroid that ended the Cretaceous, pulled up rock cores from roughly 1.5 miles below the seafloor. What they found in those cores was not what they were looking for. They were looking for evidence of the impact melt, the shocked minerals, the geological record of the collision. They found all of that, but they also found something else, something alive, microbial communities, living inside the impact-fractured rock, thriving in the hydrothermal system that the impact itself had created, a system of warm, chemically rich water circulating through the shattered and permeable rock of the crater floor. The bacteria living in those rocks were not contaminants from the drilling process. Their isotopic signatures, their cell structures, their metabolic products, all indicated organisms that had been living in the rock, in the dark, feeding on the chemical energy of the hydrothermal fluids for an extraordinarily long time. Think about what this means. The asteroid that struck 66 million years ago, the impact that killed 3/4 of all species on Earth, that ended the reign of the non-avian dinosaurs, that darkened the sky for years. That same impact created a hydrothermal system in its crater floor that became a refuge, a warm, chemically active, protected environment in a world that had gone cold and dark above. While the surface was experiencing impact winter, while the food chains were collapsing, while species after species was going extinct, something was alive in the wound itself. Something was using the energy of the catastrophe to survive the catastrophe. The Vredefort impact structure in South Africa tells a similar story, scaled up by a factor of 20 in terms of age. 2 billion years old. The hydrothermal system generated by that impact would have persisted for perhaps 1 million years after the strike. 1 million years of warm, mineral-rich, energy-rich conditions in the fractured rock of the crater floor, at a time when the surface of Earth was experiencing the Great Oxidation Event, when rising oxygen levels were toxic to most of the anaerobic life that had dominated the planet for 2 billion years. The crater was not just a wound in the rock, it was a shelter. A place where anaerobic organisms, the kind that had been running the planet's biology since the beginning, could survive the oxidation of the surface world by retreating into the warm, oxygen-free chemistry of the impact hydrothermal system. The scar as sanctuary, the catastrophe as cradle. Every time you think you understand what a geological feature means, the Earth adds another layer of meaning. And this is true not just of impact craters. Deep drilling projects around the world, in South Africa's gold mines, in the basalt of the Columbia River Plateau, in the ancient rocks of Scandinavia, have consistently found microbial life living in the rock itself. Not in water that happens to flow through the rock, in the rock, in fractures and pores at depths of 2, 3, 4 kilometers, at temperatures that would sterilize a hospital operating room, at pressures that would crush a submarine. These organisms, collectively called the deep biosphere, may represent a significant fraction of all living biomass on Earth. Some estimates suggest that the total mass of organisms living in Earth's crust rivals the mass of all surface life combined. The deep biosphere is sustained not by sunlight and photosynthesis, but by the chemistry of rock and water, the same chemistry that operates at hydrothermal vents, in impact craters, in the fractured zones along fault lines. Every scar on this planet is a potential habitat. Every fracture zone, every hydrothermal system, every impact melt sheet is an environment where something, somewhere, has found a way to extract energy and persist. This is the thing about scars. We think of them as damage, as the record of violence, of trauma, of loss. And they are all of those things. But they are also openings, literally fractures in the rock that allow fluids to circulate, that create chemical gradients, that generate the energy that life runs on. The wound opens the rock. The open rock becomes habitable. The habitable rock gets inhabited. And the inhabitant persists, sometimes for millions of years, in a world it never sees, feeding on the chemistry of a catastrophe that happened long before anything like it existed. Now let me shift your attention from the wounds that plate tectonics has inflicted on itself, the rifts, the faults, the canyon walls, to a completely different category of scar. One that comes not from within the Earth, but from beyond it, impact craters. The Earth has been struck by asteroids and comets throughout its history. We know this not just from the geological record, but from looking at other planetary bodies. The Moon's surface, unaffected by erosion or tectonics, preserves a record of impacts dating back 4 billion years. Its highlands so densely cratered that counting individual craters in some areas is nearly impossible. Mars is similarly cratered. Mercury, the moons of the outer planets. Every solid surface in the solar system that is old enough bears the marks of the bombardment that characterized the early solar system. Earth, by contrast, look almost unscathed. Find an image of Earth from space and compare it to the Moon. The Earth looks smooth, alive, unmarked. But this is deceptive. Earth has been struck just as many times as the Moon, possibly more, given its larger cross-sectional area and stronger gravitational pull. What it has done is erase the evidence. Plate tectonics recycles the ocean floor every 100 to 200 million years, destroying any craters on oceanic crust. Erosion and deposition bury or wear away craters on continental surfaces, and the atmosphere burns up the smaller impactors entirely before they reach the ground. But some craters survive. Some are so large, so deep, that even 2 billion years of geological processing has not fully erased them. And the ones that remain are among the most extraordinary features on Earth's surface. The Vredefort Dome in South Africa is the largest confirmed impact structure on Earth. The impactor that created it struck roughly 2 billion years ago. With an estimated diameter of somewhere between 15 and 25 miles, a rock the size of a small city moving at perhaps 30 miles per second. The energy released in the impact was roughly 10 billion times the energy of the Hiroshima bomb. The original crater was estimated to be nearly 200 miles in diameter. Today, after 2 billion years of erosion, what remains is a roughly 90-mile wide dome structure in the Witwatersrand Basin. The rock from the crater floor pushed upward and exposed by the erosion of the overlying material, creating a circular pattern of ancient rocks that geologists spent decades trying to explain before the impact origin was confirmed in the 1970s. The Chicxulub impact structure, buried beneath the Yucatan Peninsula and the Gulf of Mexico, is roughly 120 miles in diameter and 66 million years old. The end Cretaceous impactor that we've discussed before. But there are others. The Sudbury Basin in Ontario, Canada, 1.85 billion years old, originally perhaps 160 miles across. Now an elongated basin that has been stretched and deformed by subsequent continental collision. The Manicouagan Reservoir in Quebec, 214 million years old, roughly 60 miles in diameter, and visible from space as a nearly perfect annular ring of water surrounding a central plateau. These craters are not just interesting landforms. They are data. They are timestamps. They record the moments when something from outside the Earth arrived here with enough energy to locally vaporize the crust, melt the underlying rock, and permanently alter the geological architecture of an entire region. The Sudbury Basin is particularly significant because the heat from the impact melted enormous volumes of rock, allowing different minerals to separate by density. Dense sulfide minerals sinking to the bottom of the melt pool, lighter silicates rising to the top. The result was one of the richest concentrations of nickel, copper, and platinum group metals on Earth. The city of Sudbury exists because an asteroid struck 1.8 billion years ago. The metals in your electronics, the catalytic converter in your car, the surgical instruments in your hospital, some of that material traces back to the chemistry of an ancient impact melt. But impact craters are more than time capsules and ore deposits. They are also, and this is the part that tends to surprise people, potential nurseries for life. The intense heat of an impact melts and brecciate the target rock, creating fractured zones that can persist for millions of years. Hydrothermal systems develop in the warm, chemically altered rock of the crater floor, driven by the residual heat of the impact. Crater lakes form in the depression, often chemically rich due to the dissolved minerals in the impact melt. Several studies have found evidence of microbial communities thriving in the hydrothermally active zones of young impact craters, environments that, in some ways, parallel the conditions at mid-ocean ridge hydrothermal vents. The same event that devastates the surface can create, in its aftermath, a protected, energy-rich microenvironment where life can shelter and potentially persist through a mass extinction. The wound and the womb, written in the same rock. Now I want to bring all of these threads together: the canyon, the rift, the fault, the crater, and show you something that synthesizes them into a single, larger story. Because each of these features as extraordinary as it is individually, is a piece of a much longer narrative. The narrative of the supercontinent cycle. Earth's continents do not wander randomly. They follow a rhythm, a slow, deep rhythm with a period of roughly 500 to 600 million years. Driven by the heat engine of the mantle, the continents drift, collide, and assemble into supercontinents, enormous single landmasses where nearly all of Earth's continental crust is gathered into one place. Then the mantle heat, building up beneath the insulating blanket of the supercontinent, begins to destabilize the assembly. Rifts form. The supercontinent breaks apart. The fragments drift away from each other, opening new ocean basins between them. And eventually, hundreds of millions of years later, they come back together again, closing those ocean basins, building new mountain ranges, and assembling a new supercontinent. The cycle repeats. We know of at least 3, possibly 4, supercontinents in Earth's history. The oldest known is Ur, or Valbara, a partial supercontinent that may have existed around 3 billion years ago, though its exact configuration is debated. Then Kenorland, roughly 2.7 billion years ago. Then Columbia, also called Nuna, around 1.8 billion years ago, the period when the Vishnu basement rocks of the Grand Canyon were being cooked in its roots. Then Rodinia, around 1 billion years ago, which broke apart between 750 and 600 million years ago, perhaps triggering the snowball Earth glaciations that created the Great Unconformity. Then Gondwana and Laurasia, the 2 fragments of the next assembly, which came together as Pangaea roughly 300 million years ago. And Pangaea broke apart, beginning about 180 million years ago, producing the current configuration of continents. Each stage of this cycle produces its own signature geological features. When continents collide to form a supercontinent, they build mountain ranges, the Himalayas of their age. Thrust up by the collision of continent against continent. When supercontinents break apart, they produce rifts, like the East African Rift, but on a global scale. The Atlantic Ocean exists because Pangaea rifted. The Red Sea exists because Arabia rifted from Africa. Every ocean basin currently open on Earth is the legacy of a rift that succeeded. And within the ocean basins created by these rifts, the mid-ocean ridge system does its work, spreading the seafloor, recording the magnetic polarity of the Earth at the time each strip of crust solidified, creating the striped pattern of magnetic anomalies that geologist Harry Hess and oceanographer Marie Tharp mapped in the mid-20th century, and that provided the first definitive evidence for seafloor spreading, and ultimately for plate tectonics itself. Marie Tharp deserves a moment here. Working at Columbia University's Lamont Doherty Laboratory in the 1950s, largely excluded from participating in the research cruises that collected the data she analyzed because women were not permitted on the ships, Tharp painstakingly mapped the topography of the Atlantic Ocean floor from sonar soundings. What she found was the Mid-Atlantic Ridge, a continuous mountain range running down the center of the Atlantic, flanked by a central rift valley. Her colleague Bruce Heezen initially dismissed her interpretation as, in his words, girl talk. Within a few years, the evidence was so overwhelming that the scientific community had no choice but to accept that the seafloor was spreading, the continents were moving, and the Earth's surface was not the static backdrop that a century of geological thinking had assumed it to be. The scars on the ocean floor, the rifts, the ridges, the fracture zones, told a story that rewrote geology entirely. And they were there all along, waiting to be read. Now let me take you somewhere that connects the very deepest history of Earth's scarring to the most immediate human-scale consequences of that history, to the subduction zones. If mid-ocean ridges are where oceanic crust is born, subduction zones are where it dies. These are the places, typically at the edges of ocean basins, where oceanic crust meets continental crust or older oceanic crust, where one plate dives beneath another and descends into the mantle. Subduction zones are the most geologically violent places on Earth's surface. They produce the largest earthquakes, the most powerful tsunamis, and the most explosive volcanic eruptions. The Ring of Fire, the chain of volcanoes and earthquake zones encircling the Pacific Ocean, is, in its entirety, the product of subduction. The subduction process produces its own distinctive scars. The oceanic trench, the deep, elongated depression at the subduction zone where the descending plate bends downward before plunging into the mantle, is one of the most extreme environments on Earth's surface. The Mariana Trench in the Western Pacific reaches a maximum depth of roughly 36,000 feet, nearly 7 miles below sea level. If you placed Mount Everest at the bottom of the Mariana Trench, its summit would still be more than a mile below the water's surface. The Mariana Trench exists because the Pacific Plate, among the oldest and therefore densest oceanic crust on Earth, having been cooling and contracting since it was created at a spreading center roughly 180 million years ago, is diving beneath the Mariana Plate at the western edge of the Pacific. The angle of descent is steep, the trench deep, and the subducting slab carries with it everything that has accumulated on the Pacific seafloor over 180 million years. Sediment, altered basalt, water incorporated into hydrous minerals, and the chemical record of 180 million years of oceanic history, all of it drawn down into the mantle to be recycled, eventually returning to the surface through the volcanoes of the Mariana Arc, reborn as new material in a new form. The water is particularly important. As the subducting slab descends and heats up, the water locked in its minerals is released under pressure. This water migrates upward into the overlying mantle wedge, the piece of mantle caught between the descending slab and the overriding plate, and does something critical. It lowers the melting point of the mantle rock. Rock that would otherwise remain solid at that temperature and pressure melts in the presence of water. This melt rises, collecting in magma chambers beneath the overriding plate, and erupts as the explosive, silica-rich, gas-laden magma of the arc volcanoes. Subduction zone volcanoes are not like the gentle shield volcanoes of Hawaii, which erupt fluid basaltic lava in graceful curtains of fire. They are explosive, the magma viscous and gas-rich, prone to catastrophic decompression. Krakatoa, Pinatubo, Tambora. The eruption of Tambora in 1815 killed an estimated 70,000 people directly, and, through the year without a summer of 1816, caused by the sulfur dioxide it injected into the stratosphere, contributed to crop failures and famine across Europe and North America that killed tens of thousands more. These are not geological abstractions. They are the direct consequences of the Pacific Plate's 180 million year journey toward the Mariana Subduction Zone, carrying its cargo of water-bearing minerals down into the depths. And the earthquakes. The subduction zones of the Pacific Rim produce the largest earthquakes on Earth, mega-thrust earthquakes, where the overriding plate and the subducting slab lock together along a fault surface that can be hundreds of miles long and tens of miles wide. When that locked interface finally breaks, releasing the elastic strain that has been accumulating for decades or centuries, the energy release can be staggering. The 2004 Indian Ocean earthquake, a magnitude 9.1, the result of the Indian plate subducting beneath the Burma plate along the Sunda megathrust, ruptured approximately 750 miles of fault surface in roughly 8 to 10 minutes. The energy released was equivalent to roughly 23,000 Hiroshima bombs. The seafloor on one side of the fault lurched upward by as much as 16 feet, displacing a volume of water equivalent to a small ocean, and generating a tsunami that killed approximately 227,000 people across 14 countries. The rupture was so energetic that it measurably altered the rotation of the Earth, shortening the day by approximately 2.68 microseconds, and caused the planet to wobble slightly on its axis by about an inch. The Earth itself moved. The day became fractionally shorter, and it was all because of a scar, a subduction zone that had been quietly accumulating stress since the last time it ruptured, centuries before. But here is where I want to take the story in a direction that might surprise you. Because we have been talking about scars as records of violence, impacts, rifts, faults, subduction zones, and violence is certainly what creates them. But the scars do something else. They regulate, they stabilize, and without them, Earth as we know it would not exist. Consider the subduction zones again. As oceanic crust descends into the mantle, it carries with it the sediment that has accumulated on the ocean floor. Sediment rich in calcium carbonate, the shells and skeletons of marine organisms, the precipitation of calcium and carbon from seawater. When that carbonate-rich sediment is heated and compressed in the subduction zone, it releases carbon dioxide, which migrates upward through the overlying crust and is eventually vented to the atmosphere through the arc volcanoes. This is the geological side of the carbon cycle, the deep, slow return of carbon from the ocean floor to the atmosphere, on timescales of tens to hundreds of millions of years. Without subduction, carbon dioxide would continue to be drawn down from the atmosphere through chemical weathering and carbonate formation, but it would have no way to return. Over geological time, atmospheric CO2 would plummet. The greenhouse effect would diminish. Earth would cool permanently. The planet would freeze. Complex life would be impossible. The subduction zones, the scars of the planet, are the valves that keep the carbon cycle running. They are part of the planetary thermostat. They are not incidental features of a restless Earth. They are essential regulatory systems, without which this planet would be as cold and dead as Mars. Similarly, the East African Rift and its predecessors, the rifting events that have punctuated Earth's history throughout the supercontinent cycle, have had profound effects on climate and life. When Pangaea began to break apart 180 million years ago, the opening of new ocean basins dramatically altered the circulation of the world's oceans, changing the distribution of heat between the tropics and the poles, modifying rainfall patterns, creating new shallow water environments that life rapidly colonized. The rifting of the North Atlantic, which completed the separation of Europe and North America roughly 80 million years ago, opened a new oceanic connection that eventually helped establish the thermohaline circulation, the deep ocean current system, often called the ocean conveyor belt, that moderates the climate of the Northern Hemisphere today. And the Himalayas, the Himalayan mountain range, the scar left by the collision of India with Asia, which began roughly 50 million years ago and continues today, has arguably had more influence on the global climate over the past 50 million years than any other single geological event. As the Himalayas rose, the increased surface area of bare rock exposed to the atmosphere accelerated chemical weathering on a massive scale. Weathering consumes carbon dioxide, removing it from the atmosphere. The uplift of the Himalayas and the Tibetan Plateau has been credited by many climate scientists as a major driver of the long-term cooling trend that began roughly 50 million years ago, ultimately leading to the establishment of the Antarctic ice sheet around 34 million years ago and the onset of the Quaternary Ice Age cycle over the past 2.5 million years. The collision of two continents, a scar, and the result, over tens of millions of years, was a fundamental restructuring of Earth's climate. The world you live in, with its polar ice caps, its seasonal cycles, its temperate zones, this world is partly the legacy of a geological scar in South Asia. Now we have reached the point in the story where I want to ask you to look forward rather than backward. Because all of the processes we have discussed, the rifts opening, the plates moving, the continents drifting, are still ongoing. The clock is still running. And if we extend the geological record forward rather than backward, we can make predictions about what Earth will look like in the future. The East African Rift will continue to open. In roughly 10 million years, a narrow sea, perhaps resembling today's Red Sea, will occupy the Rift Valley. In 50 million years, a full ocean basin will separate Eastern Africa from the rest of the continent. The Red Sea will widen as Arabia drifts further from Africa. The Atlantic will continue to broaden as North America and Europe drift apart, at roughly the rate your fingernails grow, currently about 2.5 inches per year. But the Atlantic will not grow forever. At some point, perhaps in the next 100 million years, subduction will begin along its margins. The Atlantic seafloor, growing older and denser as it moves away from the mid-Atlantic ridge, will eventually become negatively buoyant enough to begin sinking. Subduction zones will form along the eastern coast of North America or the western coast of Europe. The Atlantic will begin to close. North America will begin moving back toward Europe. And eventually, perhaps 300 million years from now, perhaps 400, the Atlantic will close entirely. North America will collide with Europe and Africa, and a new supercontinent will assemble. Geologists have proposed names for this future supercontinent. The most widely discussed are Pangaea Proxima, essentially Pangaea reassembled in a similar configuration, and Amisia, a concept developed by geologist Ross Mitchell and colleagues at Harvard, which proposes that the next supercontinent will assemble around the Arctic rather than at the equator. According to the Amisia hypothesis, North America will drift northward and collide with Asia across the closing Arctic Ocean, while Africa, Australia, and Antarctica converge from the south. The result would be a supercontinent centered roughly over the current North Pole. No one alive today, no one who will ever live in any conceivable future, will see this happen. But the processes driving it are active right now. The Atlantic is opening, the Pacific is closing, the East African Rift is widening, the San Andreas is slipping northward, the Himalayas are still rising, and beneath all of it, the mantle convects, slowly, enormously, relentlessly, redistributing the heat of Earth's interior in the great engine that has been running since the planet's formation 4.5 billion years ago, and will continue running for billions of years more. The scars we have explored in this video, the Grand Canyon, the East African Rift, the mid-ocean ridges, the San Andreas Fault, the impact craters, are not just geological curiosities. They are the autobiography of a planet. They record every major event in Earth's 4.5 billion year history. They reveal the forces, internal and external, that have shaped every environment that every organism in this planet's history has ever lived in. They explain why the continents are where they are, why the oceans exist, why the atmosphere has the composition it has, why the climate has changed so dramatically over geological time, and why it will continue to change. And they carry a message that I think is worth sitting with for a moment. This planet has been through things that, by any reasonable standard, should have ended it. Impacts large enough to vaporize the crust, glaciations that covered every ocean with ice, mass extinctions that eliminated more than 90% of all species, volcanic episodes that poured out millions of cubic miles of lava and poisoned the atmosphere for millions of years. And yet, here it is, still tectonically active, still hydrologically active, still biologically active, still wearing its scars, but alive. The Grand Canyon rim at dawn, before the tourists arrive, offers something that no photograph captures: a record, not a view, not a landscape, a record. 1.5 billion years of Earth's autobiography, exposed in the walls of a canyon that a river carved through it. The Vishnu schist at the bottom was formed when no animal had yet evolved to look at it. Every layer above it is a chapter in the slow, interrupted, magnificent story of how this planet got from there to here. The same is true of every rift valley in Africa, every fault scarp in California, every oceanic trench in the Pacific, every impact crater on every continent. The Earth does not simply exist. The Earth records. It archives. It preserves, imperfectly but persistently, the evidence of everything that has happened to it, in a language that took human beings until the 20th century to even begin to read. We are still learning that language. The science of plate tectonics, remember, was not accepted by the mainstream geological community until the late 1960s. Before that, within living memory of people who are still alive today, the idea that continents moved was considered by many distinguished geologists to be pseudoscience. Alfred Wegener, the German meteorologist who proposed continental drift in 1912, based on the fit of the continents and the matching of geological formations across the Atlantic, was dismissed, ridiculed, and died in 1930 on the Greenland ice cap without seeing his central insight vindicated. It took the mapping of the ocean floor, the work of people like Marie Tharp, who was not allowed on the ships that collected her data, to reveal the mid-ocean ridges and their spreading centers, and to finally force the geological community to accept what the scars had been saying all along. The planet was trying to tell us, for decades, in the only language it has, rock. And what the rock tells us, ultimately, is something that I find genuinely humbling. The processes that created the conditions for life on Earth, the water delivered by comets and asteroids, the magnetic field generated by the liquid iron core, the plate tectonics that regulates the carbon cycle, the impacts that periodically reset the evolutionary game and open new ecological space. All of these are connected. All of them are part of a single planetary system, running on geological time, indifferent to any individual organism or species, but in some deep sense conducive to the persistence of biology. The scars are not flaws, they are features. They are the evidence of a planetary system working exactly as it should, violently, grandly, on timescales that dwarf everything we consider significant, reshaping itself endlessly in the service of no purpose whatsoever, except the blind, magnificent operation of physics, not because it was designed for life, but because the physics and chemistry of a planet the right size, at the right distance from its star, will tend over billions of years to produce and maintain the conditions that life needs. And we are the part of this system that can look at it, that can read it, that can stand at the rim of the Grand Canyon at dawn, in the cold, before the tourists arrive, and look down at 1.8 billion years of rock and feel something that has no name, but that every geologist who has ever stood there has felt. Something between awe and recognition. The recognition that you are part of this, that the calcium in your bones was forged in a star, that the carbon in your cells was once carbon dioxide in an ancient atmosphere, fixed by a photosynthesizing microbe that has been dead for hundreds of millions of years, that the iron in your blood was carried here by a comet or an asteroid, perhaps the same one that contributed to the chemistry of the hydrothermal vent, where the first replicating molecule assembled itself in the dark. You are made of the same stuff as the Vishnu schist. You are continuous with it. The scar in the canyon wall and the person looking at it are chapters in the same story. That, to my mind, is the most extraordinary thing the scars of this planet have to tell us. Not just about where the Earth has been, but about what we are.